In this tape, I would like to explain something that's called the Taylor series or Taylor expansion. And I want to give, without examples, just a very intuitive explanation why this works and what this is all about. And maybe I might approach it from a different angle, but I think it will be much easier to understand this way. The idea is that we all know about functions, and the easiest way to imagine it is a curve, some random curve on an xy plane. Everybody knows that from all the books and all the schools, that the function, the simplest way how to visualize it. And let's not kid ourselves, we're all humans and we need to visualize. Let's not get bogged down by symbolisms. So just we draw a random, as I show here, a random curve on an xy plane, and that is called a function. And there's billions or trillions or infinite kinds of curves. So the curve means the relationship, there's an x and there's a y, and then there's the way how this behaves. That can behave in bizarre ways and all kinds of cute ways and nice ways. This is the idea of an xy plane. Now, we understand that there could be, imagine you draw some kind of, you doodle on a paper some kind of bizarre curve, and your friend also doodles, and guess what? At a certain x, they both share the same y. Let's say when x, you check, and you have a graph paper, you doodle on it, your friend also doodles, and then you check when x is 17, you see that on your paper y is equal to, let's say, 45, and when your friend's paper also on that same, he also just happened to be that on his paper when x is 17, y is 45. So now somebody would comment, oh wow, you both made the same exact curve. Oh, that's a silly comment. The curve is totally different. Just on one point, on a single point, x is 17, y is 45. That's the only thing they share in common. Besides that, they're totally different. Now, how about, here where it comes some calculus, and hopefully somebody who listens to this knows a little bit of calculus. How about if somebody measures the tangent line at the point where x is 17 and y is 45? Both of your friends, and he sees, guess what? They both share also the same slope. That's the high school way of calling it same slope. Guess what happened now? These two graphs that you and your friend made became a little bit closer to each other. They resemble each other a drop more. And I want to stop right here to explain. And once you understand this thoroughly, everything gets easier. Why are they more closer related than the scenario that I said before? Because the definition of a slope at a tangent point is the idea of getting on a curve, you get the 2 points so the idea is to make 2 points and draw a line, and as they approach very close to that point, that's what defines the tangent. Anybody who knows calculus knows what I'm talking about. So when we say, here is where we have to really knock this into our brains. When we say that these two guys, besides sharing that single point on x is 17, y is 45, they also share the tangent at that point, we are in essence stating that the point a little bit above, after x is 17 and below, if you draw a line connecting them, you will get the same slope like the other guys. So that means that not only when x is 17, y is 45, when x is 16 and a half, y is blah blah, and when x is 17 and a half, y is blah blah, because we are saying that they are sharing the same slope that connects these two dots. That's a drop less than 17 or a drop more than 17. So we just caused, by this statement, we just made these graphs become even more alike. Now, if you understand this very well, we just take this logic one step further, and that is what is called the second derivative. The second derivative is simply taking this whole thing and expanding it more and more, like somebody throwing a pebble in an ocean, and it has a ripple. It's rippling all over the ocean. It goes very far. So the second derivative is just taking it a drop further. It's saying that, imagine you're taking these two, you're making two tangent lines on both of these, on your graph and your friend's graph, and then you're seeing how the relationship of these two tangents are to each other. How much do they change in their the number of their slope? How fast do they change? And that, if that's also the same, it means you're expanding this similarity to these two graphs, and actually it's increasing in a speed of the power of 2. So it gets 2, 4, 8, 16, and increases very fast. So the more you can claim that these two graphs share the derivative, the first derivative, the second, the third, the fourth, the fifth derivative are all the same, it means you are blowing a lot of air around this point, and you're saying that all these points are not necessarily the x and the y's are the same in both of these graphs. So obviously, if we could claim that this is infinite, so in other words, all the, no matter how many derivatives you'll go, if somebody can make such a claim, let's say there's some prophet, these two guys, nobody knows the function. This guy drew a random graph. Other guy in a different room drew another random graph. And there's a prophet standing next to these people, and the prophet says, I can visualize. The guy looks at the point where x is 17, y is 54, and he says, I can see that the first derivative at this point is this number, the second derivative is this, the third is this, and he keeps on talking and talking, and there's somebody that records his voice. Then there's another guy in the other room, the other prophet also keeps on talking, and guess what? The both recordings are the same, and they both talk and talk forever and ever, because they have to talk till the billionth derivative, but they all keep on saying, guess what? These two graphs are exactly the same function. They have the same curve all over the place. So we know it. We deduce this from a fact of knowing that at a single point, the derivative and the second and the third and the blah, blah, all share the same. It is from this we can conclude that they are actually the exact same graph all over the place. Now, this has amazing many implications how we can translate this. One, this is just to bring out the idea, but how we can use this and, as you say, exploit this property is an amazing thing. Why? It's an amazing thing because it means one of the implications that if the other way around you do know the function, this is just working the same thing with the other side of the coin. You know for a fact what the function, what the fx is of this whole graph. But you are too lazy to count. You know that you know what fx is at a certain point, but you don't know what's the next point. So the more derivatives you know, the more you can approximate, because we just claimed that at a certain point, if you know all the information about that point, you know everything already. So you can just keep on moving on without actually calculating the fx. So let's say you know fx, logarithm of x at point 0. Logarithm of 0 is 1. I'm sorry, logarithm of 1 is 0, because e to the 0 is 1. So logarithm of 1 is 0. Now, you want to know what the logarithm of 1.5. So you do this. Do you know what is the first derivative at the point of logarithm of 1? And that is, first of all, you have to know the rules. What's the logarithm of x is 1 over x. So the first derivative there would be 1 over 1 is 1. How about the second derivative? So we know that second derivative is of 1 over x is 1 over x squared. And again, you just put in the 1 since you're talking by point 1. So it's again 1. What's the logarithm of 1 over x squared? Is x negative 3 is 2 over x cubed. So that's, in this case, it is 2 over x cubed, so it's 2. Basically, you just have to keep on doing the math and you find out all the derivatives. From knowing the derivatives, you can figure out the more and more information about this next point that you're trying to find out the fx. Exactly how to do it, you can look in the textbooks. They tell you exactly how to manipulate these derivatives, because it's not just adding the derivatives. You gotta put them in the right form. They should make sense what you're doing. So for that, I'll refer you to the books to find out how to, after knowing the derivatives, how to use that information of getting the point that you're looking for. Thank you for listening.